Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the crisp mountain air of Southern California, perched high above the growing city of Los Angeles, stood humanity's most powerful eye on the universe. The year was 1924, and the Mount Wilson Observatory housed the world's largest telescope, a magnificent 100-inch reflector that would soon revolutionize our understanding of the cosmos itself. At this pivotal moment in astronomical history, the scientific community was embroiled in what historians now call the Great Debate. The central question that divided astronomers was deceptively simple yet profoundly important. What exactly were those mysterious spiral nebulae scattered across the night sky? Were they merely nearby clouds of gas and dust within our own Milky Way galaxy? Or were they something far more extraordinary, entire galaxies in their own right, separated from us by unimaginable distances? The debate had raged for years between two titans of astronomy. Harlow Shapley, director of Harvard College Observatory, argued passionately that these spiral nebulae were local phenomena. According to his calculations, our Milky Way galaxy was so vast that it must contain virtually everything visible in the universe. On the opposing side stood Heber Curtis of Lick Observatory, who proposed the radical idea that these nebulae were actually island universes, independent galaxies comparable in size to our own Milky Way, scattered throughout an enormously larger cosmos. Into this intellectual battleground stepped Edwin Powell Hubble, a man whose unique combination of athletic prowess, legal training, and astronomical passion would soon reshape humanity's place in the universe. Born in 1889 in Marshfield, Missouri, Hubble had initially pursued law at Oxford University as a Rhodes Scholar before ultimately following his true calling to astronomy. His arrival at Mount Wilson in 1919 coincided perfectly with the completion of the revolutionary 100-inch Hooker telescope. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The Hooker telescope represented a quantum leap in observational capability. Its massive mirror could gather 4 times more light than any previous instrument, allowing astronomers to peer deeper into space than ever before. But raw light-gathering power was only part of the story. The telescope's exceptional resolution could distinguish fine details in distant objects, while its advanced photographic plates could record images with unprecedented clarity and precision. Hubble understood that resolving the Great Debate required more than philosophical arguments. It demanded empirical evidence of the highest quality. He began systematically photographing spiral nebulae, searching for individual stars within their swirling arms. If these objects were truly distant galaxies, their constituent stars would appear as mere points of light, barely distinguishable from the background glow. But if they were nearby nebulae within our own galaxy, individual bright stars should be clearly visible. Night after night, Hubble guided the massive telescope across the sky, methodically building a photographic survey of spiral nebulae. The work was painstaking and often frustrating. Photographic plates required hours-long exposures to capture enough light from these faint objects, and even the slightest vibration or atmospheric turbulence could ruin an entire night's work. The breakthrough came in October 1923, when Hubble turned his attention to the Andromeda Nebula, designated Messier 31 in astronomical catalogues. This spiral nebula was among the largest and brightest visible from Earth, making it an ideal target for detailed study. As Hubble examined his latest photographic plates of Andromeda, he noticed something extraordinary: individual points of light that varied in brightness over time. These were variable stars, and their discovery would unlock the distance to Andromeda and forever change our understanding of the universe's true scale. The story of humanity's expanding universe begins with the rhythmic pulsing of ancient stars. As Edwin Hubble scrutinized his photographic plates of the Andromeda Nebula throughout late 1923, he noticed certain stars that seemed to brighten and fade in regular cycles. These were not ordinary stars. They were Cepheid variables, stellar lighthouses whose periodic pulsations would provide the key to measuring cosmic distances. Cepheid variable stars had been discovered decades earlier, but their true significance was revealed through the groundbreaking work of Henrietta Swan-Leavitt at Harvard College Observatory. Working with photographic plates of the Small Magellanic Cloud, Leavitt had discovered a remarkable relationship in 1912. The brighter a Cepheid variable star appeared at its peak luminosity, the longer its pulsation period. This period-luminosity relationship, known as Leavitt's law, provided astronomers with their first reliable standard candle for measuring distances across the cosmos. The physics underlying Cepheid pulsations involves a delicate balance between stellar gravity and radiation pressure. These evolved stars have exhausted the hydrogen fuel in their cores and begun fusing heavier elements. The resulting instability causes their outer layers to expand and contract rhythmically, like a cosmic heartbeat. Crucially, the period of this pulsation depends directly on the star's intrinsic brightness, its absolute magnitude, rather than how bright it appears from Earth. Hubble immediately recognized the profound implications of finding Cepheids in Andromeda. By measuring their apparent brightness and pulsation periods, he could calculate their absolute brightness using Leavitt's relationship. Comparing absolute and apparent brightness would then reveal their distance through the inverse square law of light propagation, a fundamental principle stating that apparent brightness decreases with the square of distance. The calculations required meticulous precision. Hubble measured pulsation periods ranging from 10 to 40 days for different Cepheids in Andromeda. He carefully calibrated his photographic plates to determine accurate apparent magnitudes, accounting for atmospheric extinction and instrumental effects. The period-luminosity relationship indicated these stars possessed absolute magnitudes, between -2 and -6, meaning they were intrinsically very bright, comparable to hundreds or thousands of ordinary stars like our Sun. When Hubble applied the distance formula, the results were staggering. The Cepheids in Andromeda appeared approximately 1 million times fainter than they would if located at a standard reference distance. This meant Andromeda lay roughly 1 million light-years away, far beyond the boundaries of our Milky Way galaxy, which astronomers estimated to be only 100,000 light-years in diameter. The implications reverberated through the astronomical community like an intellectual earthquake. If Andromeda was indeed a separate galaxy at such an enormous distance, it must be comparable in size to our own Milky Way to appear as large as it does in the sky. This meant the universe contained not just one galaxy, but potentially billions of such island universes scattered throughout space. Hubble's discovery vindicated Heber Curtis's position in the Great Debate, while revealing that even Curtis had underestimated the true scale of the cosmos. The universe was not merely larger than previously imagined. It was almost incomprehensibly vast, filled with galaxies separated by distances that dwarfed anything in human experience. But Hubble's work was far from complete. Having established that spiral nebulae were indeed external galaxies, he began systematically measuring distances to other spiral systems using the same Cepheid technique. Each new measurement extended humanity's cosmic horizon further, revealing a universe populated by countless galaxies stretching in all directions. The technical challenges were immense. Cepheids in more distant galaxies appeared progressively fainter, requiring longer photographic exposures and more sensitive techniques. Hubble pushed the 100-inch telescope to its limits, often working through entire nights to capture enough light from these remote stellar beacons. By 1925, Hubble had measured distances to nearly 24 spiral galaxies, ranging from several 100,000 to several million light-years away. Each measurement represented weeks or months of painstaking observation and calculation. Yet these efforts were laying the foundation for an even more profound discovery, one that would reveal the universe itself to be in motion, expanding at an ever-increasing rate that defied all previous expectations about the nature of cosmic space and time. While Edwin Hubble was revolutionizing astronomy through distance measurements, another piece of the cosmic puzzle was emerging from an unexpected source. At Lowell Observatory in Arizona, astronomer Vesto Melvin Slipher had been conducting a different kind of investigation that would prove equally transformative. Using spectroscopy, the analysis of light broken down into its component colors, Slipher was discovering something peculiar about the light from spiral nebulae. Spectroscopy relies on a fundamental principle of physics. Every chemical element absorbs and emits light at specific wavelengths, creating unique fingerprints in the electromagnetic spectrum. When astronomers pass starlight through a spectrograph, they observe dark absorption lines at precise wavelengths corresponding to elements like hydrogen, helium, and calcium. These spectral lines serve as cosmic barcodes, revealing not only what distant objects are made of, but also how they are moving through space. The key to understanding galactic motion lies in the Doppler effect, a phenomenon familiar to anyone who has heard an ambulance siren change pitch as it passes by. When a source of waves moves toward an observer, the waves are compressed, resulting in higher frequency or shorter wavelength. When the source moves away, the waves are stretched to lower frequency or longer wavelength. For light, this translates to a shift toward the blue end of the spectrum, for approaching objects, and toward the red end for receding ones. Slipher began his spectroscopic survey of spiral nebulae in 1912, initially seeking to understand their composition and structure. What he found instead was far more puzzling. The spectral lines in galaxy after galaxy were systematically shifted toward longer, redder wavelengths. This redshift indicated that virtually every spiral nebula was moving away from Earth at tremendous speeds, velocities of hundreds or even thousands of miles per second. The technical challenges of galactic spectroscopy were formidable. Spiral nebulae appeared extremely faint compared to individual stars, requiring exposure times of 20 to 40 hours spread across multiple nights. Slipher had to guide his telescope with extraordinary precision, keeping the galaxy's light perfectly aligned with the narrow entrance slit of his spectrograph for hours at a time. Atmospheric turbulence, mechanical vibrations, and even slight temperature changes could ruin an entire observation. By 1925, Slipher had measured redshifts for 45 spiral nebulae. The results were remarkably consistent. With only a few exceptions, every galaxy showed significant redshift, indicating recession velocities ranging from several hundred to over 1,000 miles per second. The few exceptions were nearby objects like the Andromeda Galaxy, which showed a slight blue shift, indicating it was actually approaching our Milky Way. These observations presented astronomers with a profound mystery. Why should distant galaxies be racing away from us at such enormous speeds? Was Earth somehow located at the center of a cosmic explosion, with galaxies fleeing in all directions? This seemed to violate the Copernican principle that Earth holds no special position in the universe. The redshift phenomenon became even more intriguing when combined with Hubble's distance measurements. Slipher's fastest-moving galaxies tended to be among the faintest and most difficult to observe, suggesting they might also be the most distant. If this correlation held true, it would imply a systematic relationship between distance and recession velocity, a pattern that could reveal fundamental properties of the universe itself. Hubble recognized the potential significance of combining his distance measurements with Slipher's velocity data. If distant galaxies were indeed receding faster than nearby ones, this would suggest something extraordinary about the nature of space itself. Rather than galaxies moving through static space, perhaps space itself was expanding, carrying galaxies, along like raisins in rising bread dough. The theoretical groundwork for such an interpretation already existed. In 1915, Albert Einstein had published his general theory of relativity, which described gravity not as a force, but as the curvature of space-time itself. Einstein's equations predicted that the universe could not remain static. It must either expand or contract under its own gravitational influence. Initially, Einstein had been troubled by this prediction and introduced a cosmological constant to maintain a static universe. However, by the mid-1920s, theoretical physicists like Alexander Friedmann and Georges Lemaitre were exploring solutions to Einstein's equations that described expanding universes. These models predicted exactly the kind of distance velocity relationship that seemed to be emerging from astronomical observations. The stage was now set for one of the most important discoveries in the history of science. Hubble had the tools to measure accurate distances to distant galaxies, while Slipher had demonstrated their systematic recession. All that remained was to combine these observations systematically and reveal the mathematical relationship that would forever change humanity's understanding of the cosmos. The year 1929 marked a watershed moment in humanity's understanding of the cosmos. Edwin Hubble, now armed with distance measurements to 24 galaxies and velocity data from Vesto Slipher's spectroscopic observations, began the systematic analysis that would reveal one of the universe's most fundamental properties. Working at his desk in the Mount Wilson Observatory offices, surrounded by photographic plates and calculation sheets, Hubble was about to uncover a mathematical relationship that would revolutionize cosmology. Hubble's approach was methodical and precise. He plotted each galaxy's recession velocity, derived from its redshift against its distance, calculated using Cepheid variables and other distance indicators. The initial dataset was modest by today's standards: 24 galaxies with distances ranging from approximately 1 million to 6 million light-years, and recession velocities spanning from 100 to 1,000 miles per second. As Hubble examined his scatterplot, a remarkable pattern emerged. Despite the inevitable uncertainties in both distance and velocity measurements, the data points showed a clear linear trend. Galaxies twice as far from Earth were receding twice as fast. Galaxies 3 times more distant were moving away 3 times faster. This was not coincidence. It was evidence of a fundamental law governing the behavior of the universe itself. The mathematical relationship could be expressed with elegant simplicity: velocity equals distance multiplied by a constant. In scientific notation, this became v sans hxd, where v represents recession velocity, d represents distance, and h represents what would later be known as the Hubble constant. This proportionality constant described the rate at which the universe was expanding, measured in units of velocity per unit distance. Hubble's initial calculation yielded a value of approximately 300 miles per second per million light-years for his constant. This meant that for every additional million light-years of distance, galaxies receded an additional 300 miles per second faster. The implications were staggering. This relationship suggested that the entire universe was expanding uniformly in all directions. The discovery contradicted every previous assumption about the cosmos. For millennia, philosophers and scientists had envisioned the universe as static and unchanging on the largest scales. Even Einstein, whose equations predicted cosmic expansion, had initially rejected this possibility as physically unreasonable. Yet here was observational evidence that space itself was stretching, carrying galaxies along like markers on an inflating balloon. Hubble's law also resolved the puzzle of why Earth appeared to occupy a special position at the center of cosmic recession. In an expanding universe, every observer would see the same pattern: distant galaxies receding faster than nearby ones. This was a consequence of the uniform expansion of space rather than any special property of our location. An astronomer on any galaxy would observe the same linear relationship between distance and recession velocity. The theoretical framework for understanding this expansion already existed. Alexander Friedmann's solutions to Einstein's field equations described homogeneous isotropic universes that could expand or contract over time. Georges Lemaitre had independently derived similar solutions and even predicted the linear distance-velocity relationship that Hubble was now confirming observationally. Lemaitre's work went further, suggesting that an expanding universe implied a moment of cosmic beginning, a primeval atom from which all matter and energy had emerged. This concept would eventually evolve into what cosmologists now call the Big Bang theory, describing the universe's origin from an extremely hot, dense initial state approximately 13.8 billion years ago. Hubble himself remained cautious about the cosmological implications of his discovery. As an observational astronomer, he focused on accurately measuring distances and velocities rather than speculating about theoretical models. He continued referring to galactic redshifts as apparent recession velocities, acknowledging that other explanations might eventually emerge. Nevertheless, the observational evidence for cosmic expansion grew stronger as Hubble extended his survey to more distant galaxies. Each new measurement reinforced the linear relationship, while improved distance calibrations refined the value of the Hubble constant. By the early 1930s, the expanding universe had gained acceptance among most astronomers and physicists. The discovery of Hubble's law marked the birth of modern cosmology as a quantitative science. For the first time, astronomers could measure the universe's expansion rate and extrapolate backward to estimate its age. They could test theoretical models against observational data and make predictions about cosmic evolution. The universe had revealed itself to be dynamic, evolving and governed by mathematical laws that human intelligence could comprehend and explore. The implications of Hubble's discovery rippled through science like waves from a cosmic explosion. If the universe was indeed expanding uniformly in all directions, this fundamental observation opened entirely new avenues of inquiry about the nature of space, time, and existence itself. Scientists were forced to confront questions that had previously belonged to the realm of philosophy and theology. Did the universe have a beginning? How old was it? What would be its ultimate fate? The concept of cosmic expansion challenged fundamental assumptions about the nature of space. In classical physics, space was viewed as an absolute, unchanging stage upon which cosmic events unfolded. Einstein's general relativity had already modified this picture by showing that massive objects could curve spacetime. But the idea that space itself could expand was revolutionary. Galaxies were not racing through static space. Rather, space itself was stretching, carrying galaxies along like dots drawn on an inflating balloon. This expanding space interpretation resolved several puzzling aspects of galactic redshifts. It explained why virtually every distant galaxy showed recession velocities, why the recession rate increased with distance, and why Earth did not occupy a special position at the center of cosmic expansion. Every point in an expanding universe would observe the same pattern of recession velocities, making all locations equivalent in cosmic terms. The expanding universe also implied something profound about cosmic time. If galaxies were currently moving apart, then extrapolating backward in time suggested they must have been closer together in the past. Continuing this logic to its ultimate conclusion led to a startling prediction. At some finite time in the past, all matter in the universe must have been compressed into an extremely dense, hot initial state. Hubble's measurements allowed astronomers to estimate when this cosmic beginning might have occurred. By taking the reciprocal of the Hubble constant, they could calculate the time required for galaxies to reach their current separations starting from zero distance. Using Hubble's original value of approximately 300 miles per second per million light-years, this calculation yielded an age of roughly 2 billion years for the universe. This estimate immediately created what became known as the age crisis in cosmology. Geological evidence suggested that Earth itself was approximately 4 billion years old, while stellar evolution models indicated that some stars were even older. How could the universe be younger than its own contents? This apparent contradiction would plague cosmology for decades until improved distance measurements revealed systematic errors in early Hubble constant determinations. Despite these challenges, the expanding universe model made testable predictions that could be verified through further observations. If the universe had evolved from a hot, dense initial state, distant galaxies should appear younger and more primitive than nearby ones, since their light had traveled longer to reach Earth. The cosmic expansion should also leave observable signatures in the distribution of matter and the background radiation permeating space. The discovery also raised profound questions about the universe's geometry and ultimate fate. General relativity predicted that cosmic expansion could follow different evolutionary paths depending on the total density of matter and energy. If the universe contained enough matter, gravitational attraction would eventually halt expansion and cause cosmic contraction, the Big Crunch scenario. If matter density was insufficient, expansion would continue forever, leading to a cold, empty cosmos in the distant future. Determining which scenario described our universe required accurate measurements of both the expansion rate and the total matter density. Hubble's law provided the expansion rate, but measuring cosmic matter density presented enormous technical challenges. Most matter in the universe appeared to be dark, detectable only through its gravitational effects rather than electromagnetic radiation. The expanding universe also had implications for fundamental physics. If all matter and energy were once compressed into an extremely small volume, temperatures and pressures would have been unimaginably extreme. Under such conditions, the familiar laws of physics might break down, requiring new theories to describe matter and energy behavior. This insight would eventually lead to the development of particle cosmology, linking the largest scales of the universe to the smallest scales of elementary particles. Hubble's discovery marked the beginning of precision cosmology, transforming the study of the universe from philosophical speculation to quantitative science. Astronomers could now measure cosmic parameters, test theoretical models, and make predictions about cosmic evolution. The universe had revealed itself to be not just vast and ancient, but dynamic and evolving according to mathematical laws that human intelligence could discover and understand. The implications extended beyond science to philosophy and human self-perception. Humanity found itself inhabiting a cosmos that was not only larger than previously imagined, but actively changing and evolving. This dynamic universe suggested that our existence was part of a vast cosmic story, with chapters extending billions of years into the past and future. The decades following Hubble's groundbreaking discovery witnessed a continuous refinement of cosmic distance measurements and a corresponding evolution in our understanding of the universe's expansion rate. What began as a simple linear relationship between distance and recession, velocity gradually revealed itself to be far more complex, requiring increasingly sophisticated observational techniques and theoretical frameworks. The first major revision to Hubble's results came in the 1940s and 50s through the work of Walter Baade at Mount Wilson Observatory. Baade discovered that Cepheid variable stars actually comprised two distinct populations with different intrinsic properties. Population Cephids, found in the spiral arms of galaxies, were relatively young, metal-rich stars. Population 2. Cepheids, located in galactic halos and globular clusters, were older and metal-poor, with systematically different period luminosity relationships. This discovery had profound implications for cosmic distance measurements. Hubble had unknowingly calibrated his distance scale using population 1 Cephids in nearby galaxies, but many of the Cephids he observed in more distant galaxies were actually population 2 stars. Since population 2 Cepheids were intrinsically fainter than their population 1 counterparts, galaxies containing them were actually more distant than Hubble had calculated. When Baade recalibrated the cosmic distance scale accounting for these two Cepheid populations, the results were dramatic. Distances to nearby galaxies roughly doubled, which meant the Hubble constant was approximately half its originally calculated value. Instead of 300 miles per second per million light-years, the expansion rate appeared to be closer to 150 miles per second per million light-years. This revision had an immediate impact on the age crisis that had troubled cosmologists for decades. A smaller Hubble constant implied a slower expansion rate and therefore a greater age for the universe. The revised calculations suggested the cosmos was approximately 4 billion years old enough to accommodate the ages of Earth and the oldest known stars. Further refinements continued throughout the latter half of the 20th century as astronomers developed new distance measurement techniques. Alan Sandage, Hubble's successor at Mount Wilson, spent decades improving the calibration of the cosmic distance ladder, the sequence of overlapping measurement methods used to determine distances to increasingly remote objects. The distance ladder begins with direct geometric measurements using parallax for nearby stars, extends to Cepheid variables for nearby galaxies, and reaches the most distant objects through standard candles like type Ia supernovae. Each rung of this ladder must be carefully calibrated against the previous one, and uncertainties at each level compound as astronomers attempt to measure ever greater distances. Type Ia supernovae emerged as particularly valuable standard candles for measuring distances to very remote galaxies. These stellar explosions occur when white dwarf stars accrete matter from companion stars until they reach a critical mass threshold and explode with remarkably consistent peak brightness. Since they can be observed across billions of light years, Type Ia supernovae provided a way to extend Hubble's law to much greater distances than possible with Cepheid variables. The development of space-based telescopes revolutionized distance measurements by eliminating atmospheric distortions that limited ground-based observations. The Hubble Space Telescope, launched in 1990, could resolve individual Cepheid variables in galaxies tens of millions of light-years away, far beyond the reach of ground-based instruments. This capability allowed astronomers to calibrate intermediate distance standard candles with unprecedented precision. By the late 20th century, systematic surveys using space telescopes and advanced ground-based instruments were converging on a Hubble constant value of approximately 70 kilometers per second per megaparsec, equivalent to about 43 miles per second per million light-years. This implied a universe age of roughly 14 billion years, comfortably accommodating all known cosmic constituents. However, precise measurements also revealed unexpected complexities in cosmic expansion. The relationship between distance and recession velocity remained linear over vast ranges, but subtle deviations suggested that the expansion rate itself was changing over cosmic time. Most surprisingly, observations of very distant Type Ia supernovae in the late 1990s indicated that cosmic expansion was actually accelerating rather than slowing down as expected. This discovery of cosmic acceleration led to the inference that approximately 70% of the universe consists of dark energy, a mysterious component that exerts a repulsive gravitational effect, driving space to expand at an ever-increasing rate. The remaining 30% comprises matter, both visible and dark, with ordinary atomic matter making up only about 5% of the cosmic inventory. Modern measurements of the Hubble constant using different techniques sometimes yield slightly different values, leading to what cosmologists call the Hubble tension. Space-based observations of the cosmic microwave background, radiation left over from the early universe, suggest an expansion rate of about 67 kilometers per second per megaparsec, while direct measurements using Cepheids and supernovae yield values closer to 73 kilometers per second per megaparsec. Edwin Hubble's discovery of cosmic expansion stands as one of the most transformative revelations in human history, fundamentally altering our understanding of existence itself. From his initial observations at Mount Wilson Observatory nearly a century ago, the expanding universe has evolved into the cornerstone of modern cosmology, supporting an elegant theoretical framework that describes the cosmos from its earliest moments to its ultimate fate. Today's standard model of cosmology, known as lambda CDM, lambda cold dark matter, builds directly upon Hubble's foundational observations. This model describes a universe that began in an extremely hot, dense state approximately 13.8 billion years ago and has been expanding and cooling ever since. The lambda represents dark energy, the mysterious component driving cosmic acceleration, while CDM refers to cold dark matter, invisible particles that provide the gravitational scaffolding for cosmic structure formation. Modern, space-based observatories have extended Hubble's observations to unprecedented scales and precision. The Hubble Space Telescope, fittingly named in his honor, has measured distances to galaxies billions of light-years away, while the James Webb Space Telescope peers even deeper into space and time. These instruments reveal galaxies as they appeared when the universe was only a few 100 million years old, providing direct observational evidence for cosmic evolution predicted by expanding universe models. The cosmic microwave background, discovered in 1965, provides perhaps the most compelling confirmation of the expanding universe paradigm. This faint radiation, detected uniformly across the sky, represents the afterglow of the Big Bang, light from when the universe first became transparent, approximately 380,000 years after its beginning. Precise measurements of this background radiation reveal tiny temperature fluctuations that seeded the formation of galaxies and larger cosmic structures. Hubble's law has evolved from a simple linear relationship to a more complex description of cosmic expansion history. Modern cosmologists describe expansion using the scale factor, a quantity that characterizes how distances between galaxies change over time. The Hubble parameter, now recognized as time-dependent, describes the instantaneous expansion rate at any cosmic epoch. The discovery of cosmic acceleration in 1998, recognized with the Nobel Prize in Physics, in 2011, revealed that the universe's expansion history is more complex than originally envisioned. Rather than steadily slowing due to gravitational attraction, expansion has been accelerating for the past several billion years. This acceleration implies that dark energy dominates the cosmic energy budget, comprising approximately 68% of everything in the universe. Current observations suggest several possible scenarios for the universe's ultimate fate. If dark energy remains constant, expansion will continue accelerating indefinitely, leading to a cold, empty cosmos in the far future as galaxies drift beyond each other's observable horizons. Alternative models predict that dark energy might evolve over time, potentially leading to different cosmic destinies, ranging from continued acceleration to eventual contraction. The precision of modern cosmological measurements has reached remarkable levels. The Hubble constant is now known to within a few percent. The universe's age is determined to be 13.8 billion years, with an uncertainty of only 50 million years, and the relative abundances of different cosmic components are constrained to high accuracy. These achievements represent the culmination of nearly a century of observational and theoretical progress initiated by Hubble's pioneering work. Hubble's legacy extends beyond specific measurements to encompass a fundamental shift in humanity's cosmic perspective. His discovery revealed that we inhabit a dynamic, evolving universe with a definite history and potentially predictable future. This insight has profound implications for how we understand our place in the cosmos and our connection to the fundamental forces shaping space and time. The expanding universe has also catalyzed connections between cosmology and particle physics, leading to insights about the fundamental nature of matter, energy, and space-time. Theories of cosmic inflation propose that the observable universe underwent a brief period of exponential expansion during its first fraction of a second, explaining the large-scale uniformity observed in the cosmic microwave background. Modern cosmology continues to grapple with profound mysteries that emerged from Hubble's initial discovery. The nature of dark matter and dark energy remains unknown despite their apparent dominance in the cosmic inventory. Understanding these components represents one of the most significant challenges facing 21st century science. As we look toward the future, new generations of telescopes and instruments promise to further refine our understanding of cosmic expansion. Ground-based surveys will map billions of galaxies across cosmic time, while space missions will probe the universe's earliest epochs with unprecedented sensitivity. These observations will test our current cosmological model and potentially reveal new physics governing the universe's behavior. Edwin Hubble's revelation that we live in an expanding universe remains one of humanity's greatest intellectual achievements, transforming our species from inhabitants of a static cosmos to witnesses of cosmic evolution on the grandest possible scale. His legacy continues to inspire new discoveries and deepen our appreciation for the magnificent, dynamic universe we call home.